Yeah, okay. So, welcome back. Wait, everybody said. Yeah, so I want to start with the third chapter, and now we come to the part about what we actually know about gravitation and quantum mechanics. We discuss non-relativistic particles. In a Newtonian gravitational potential. And so there have been 2 experiments so far that have been done with quantum systems in the gravitational field. So there are 2 experiments where both gravity and quantum effects play a role in order to evaluate the outcome of the experiment. Both of these experiments have originally been done with neutrons. The first experiment we want to discuss is this famous cow experiment, named after the people who performed it, Colella, Oberhauser, and Werner. So completely unrelated to the animal with the equal name. So that's the first experiment, and then I will come later to a second experiment, which was also with neutrons in the gravitational field, where the energy eigenstates were measured. We will come back to that. This experiment, so I say there are these 2 experiments that have been done because, I mean, there are several other experiments, but they are basically just variations of this experiment. So there are similar experiments with atoms, but yeah, it's in principle from the theoretical description. That's the same kind of experiment. So you see, I showed you a picture of the experimental setup. So the way the experiment works is, well, it's a simple interferometer. You have one solid crystal that's made out of one block of silicon, and you have your neutrons, flying through that, and basically you have these 3 ears there, and on each of those you have Bragg reflections, so that the path of your neutron actually splits up in a superposition at this point A, and then at the points B and C you have the paths going together again. You ignore the parts that go away, and you recombine them at this point D. And of course, as you know, you get an interference pattern there. And now this experiment is done in the gravitational field of the Earth, or in the Newtonian gravitational potential. So gravity is modeled in this case simply by a potential minus mgx, which is like the naive thing we would write down, right? So basically we have the Schrödinger equation with this potential. So we just have the free Schrödinger equation, so minus mgx psi. That's kind of what you would naively write down if you know Newtonian gravity. You know how quantum mechanics works with potentials. But before this experiment has been performed, it wasn't really clear if that's really the right description of a quantum system in a gravitational field. Right? So it turns out that this is correct. So let's try to show what happens here. So we should first, for a general potential, discuss what actually happens in this interferometer. So you start with some wave function, and in the free case where this potential is 0, so for v equals 0, we have just a plane wave solution. So we have a wave function psi 0 that is e to the I kr, and then it has the usual e to the I omega t time dependence. And now we assume that our potential energy, since we are talking about gravity, and gravity is usually weak, is much smaller than the kinetic energy of our particle. So we can treat the system perturbatively, like around the free evolution. So we make an ansatz for our wave function that it is this unperturbed solution psi 0, and it gets some phase variation I to the alpha, which is a function of position. So we assume that this function alpha varies slowly with distance. So meaning that the derivative, so the gradient of alpha, is small, and therefore higher order derivative terms are completely negligible. So Laplace alpha terms are negligible. So now we just plug this in our Schrödinger equation. So we get IH bar psi dot psi 0 dot e to the I alpha r equals. So this is minus h bar squared divided by 2m. Gradient of psi 0 e to the I r. This is just using the free Schrödinger equation, right? So we just multiplied the Schrödinger equation with e to the I alpha here. And now we use the Schrödinger equation with the potential. So we have minus h bar squared divided by 2m Laplace. And now the Laplace operator is acting on the whole perturbed wave function psi 0 I to the alpha r plus the potential. Okay. So our potential is also small. So our potential is also of a higher order. So at the first relevant correction, we get the following equation. We get 0 equals minus h bar squared divided by m. Then we get okay. So the zeroth order equation is just the free Schrödinger equation, right? So we take this equation now. When the Laplace operator is acting on psi 0 here, we get this term again. So we can cancel that on both sides. That's why we get 0. And then we get the term where one of the gradients is acting on the E function. So we get gradient psi 0 times the gradient of e to the I alpha minus, then we get h bar squared divided by 2m psi 0 Laplace e to the I alpha of r plus v psi 0 e to the yes, and now we apply these derivatives, so we get h bar squared divided by m psi 0 k not gradient alpha e to the I alpha of r. So just using r psi 0 minus h bar squared divided by 2m psi 0, and then we get the gradient of I times gradient alpha e to the I alpha of r plus, and this term we can just copy. And now all that remains is actually this term and this term, because this one is, so here we get a higher derivative term, so this we can ignore. So all we have left is h bar squared divided by m psi 0 k gradient alpha e to the I alpha plus v psi 0 to the I alpha. Or, and I write this here, no? Or we can write this as k product with alpha gradient equals minus m divided by h bar squared v. Okay, so we have to, in principle, to get, so we want to get the phase now, the phase alpha that our wave function acquires while it goes along this path, right? So we have to integrate this equation along this path. So we get alpha of r equals minus the integral p denotes our path, m divided by h bar squared v, and I call d tau the parameter that parameterizes this path. And then by using Stokes' theorem, we can show that this just means that the phase shift. So if we have this path, so where we go ACD or ABC on the other hand, then the phase difference that we get is basically just integrating around the path on a closed curve. So we can use Stokes' theorem to get that this is just minus mg times the area that's enclosed by this path divided by h bar times the velocity. So yes, okay. So this is the equation that we have for an interferometer that is perpendicular to the ground, right? If this plane ABCD is perpendicular to the ground, then gravity is acting with its full strength G basically. And then what is done in the experiment to show the gravitational field is that this interferometer is actually rotated around this axis that is shown here. so that the effective area actually that's really perpendicular to the ground changes. So what we get is, instead of this G, we get the factor sine of alpha here, sine of phi, which is the rotation angle by which our experiment is rotated. So, yeah. And this is the result from when they actually performed this experiment. You also have the reference here, and you see that it's more or less what the theory predicts. Right? So you really see those oscillations of this angle phi. So you see that there is a phase shift that depends on the rotation angle, so a phase shift due to the gravitational field. Okay. The second experiment, and for this I go to the next slide first. The second experiment was done much later in the 2000s. Is considering the eigenstates of neutrons in the potential that is made up from the gravitational potential of the Earth, and then you have a reflecting mirror on the ground. So you have your neutrons, and at the top you see the actual setup of the experiment. So you shoot the neutrons in this tiny slit of your experiment. And then this mirror at the bottom reflects them. But on the other hand, gravity is acting, so they are basically trapped in this potential of gravitational force and this reflection of the mirror. So two. Eigenstates in the gravitational field. So what we have is a stationary Schrödinger equation. I think I'm a bit inconsistent with which labels I put to which direction. So Z is now the direction of the gravitational force. So we have a stationary Schrödinger equation with a potential that is just the gravitational potential, mgz, for positive Z values. And it's infinite for negative Z values. So that's the potential these particles are trapped in. And then we can calculate the eigenstates in this potential. So for that, it's convenient to introduce a coordinate theta, which is Z divided by Z0 minus E divided by mg Z0, where the Z0 is defined as h bar squared divided by 2m squared g to the 1/3. So if you use this, so then first of all, with this variable, the minus h bar squared divided by 2m e squared by d z squared can be rewritten as this is theta by dz squared. Okay, if we insert this, then we get that this is minus mg squared. Sorry, I should, okay, but, so we get minus, okay, here we will get, we have that 0, so we have this 1 power 1/3, so we should take that out. So we can write this as h bar to the 6 divided by 8m to the 3, and then we have times 4m 4g squared divided by h bar to the 4. So, so this is minus, and then we have mg squared h bar squared half to the 1/3. And this we can actually then rewrite again using h0. So this is just yes. This is minus mg z0 d squared by d squared. Okay. So with this, then the Schrödinger equation becomes really easy. It's just so, well, okay, we also replace the wave function, right? So we introduce the function chi of theta, which is the wave function evaluated at the position theta z0 plus e divided by mg. And this function now, if we insert that in the Schrödinger equation, just satisfies the following equation: the second derivative minus theta chi of theta equals 0. And this equation is well known. That's the so-called Airy differential equation, which has the Airy functions as solutions. So the Airy functions of theta are defined as 1 divided by pi, integral 0 to infinity, and then cosine t to the third plus theta t dt. So those are the solutions of this equation. And I mean, you kind of see them plotted here already, but so that's what the Airy function actually looks like, in case you haven't seen it before. So the solutions we end up with are then, in this case, Saya said, if we resubstitute now, is Airy function of z minus zn divided by z0, where, well, z0 we have already defined, but the zn is defined by energy eigenvalues En equals mg zn. And and now the thing we have to consider is that the boundary condition at 0 must be satisfied. So we need to choose our En or our Zn such that the Airy function, or that this function has the values of psi of 0 equals 0. So that means that this Zn has to be Z0 3 pi half n minus 1/4. Sorry. Yes. Oh, bigger. Yes. 3 pi half. Big enough? I try to stay that way. N minus 1/4 to the 2/3. Yeah. It's really hard to see yourself when you write something. You have to step back a bit. Okay. So, and this we can insert in the energy to get the energy eigenvalues, which are then okay, square root m half times 3 half times pi h bar g n minus 1/4, and that whole thing to the power 2/3. Okay. So if you actually insert G and insert the mass of a neutron, which is 1.7 times 10 to the minus 27 kilograms, then you get for the first values you get 1 equals 1.4 times 10 to the minus 12 electron volts, and for the second one, you get 2.5 times 10 to the minus 12 and so on. So I have another picture of that. So that's their result, right? So the line there basically shows this energy value, so it shows how the how dependent on this absorber height this curve approaches this energy eigenstate at exactly these values. Okay. So that concludes the part about what has been done so far about gravity and quantum mechanics. So everything beyond that is experimentally untested. I mean, there are some arguments sometimes, right? I mean, people talk sometimes about atomic clocks, for example. When you have atomic clocks in the gravitational field, you use atomic clocks to measure things like time dilation or something. So that's also a quantum system in the gravitational field, right? But then, I mean, in principle, everything is a quantum system in the gravitational field. The point of the clock is that the effect that you're measuring has nothing to do with the quantum properties of the clock, right? I mean, the fact that it's a quantum clock makes it have a higher precision, but the time it shows is still like just the classical time variable. It just has a higher precision to show this time variable. So as far as experiments are concerned that involve both gravity and quantum mechanics, those two types of experiment are basically the whole story. Are there any questions to that before I start with the fourth chapter? Chapter 4 is the equivalence principle. Yeah. In classical and in quantum mechanics, I saved the time now to write that out. So just as a quick introduction, I want to talk about the equivalence of inertial and gravitational mass. So basically the equivalence principle in Newtonian gravity. So in principle, there are three different types of masses in our theory. We know that we have an inertial mass, that is basically the resistance of a particle to acceleration, right? Or how fast will a particle move given a certain momentum. So this is expressed by Newton's law, F equals inertial mass times acceleration. Then we have the passive gravitational mass. That's the mass that tells, or that's basically the coupling parameter of a particle to the gravitational field, right? So given a gravitational field, how strong will a particle couple to this field? So in Newtonian gravity, that would mean that the gravitational force is mgp, I call that, for gravitational passive mass, times the gradient of the gravitational potential. So just the same as the charge in electrodynamics. And finally, we have the active gravitational mass, which is the mass with which a particle sources the gravitational field. Right? So that the mass that enters in the potential, either the Poisson equation for the potential, or if we write it out, the potential minus G M active gravitational, MGA, divided by distance. So in principle, there is no reason why those masses should be the same. So yeah. 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 Yeah, I'm coming to that. Yeah, I guess just let me. So the reason why we have the active and passive gravitational mass the same is basically just given by Newton's third law, right? So there is no need for equivalence principle there. So we know that if we have two particles, then the force that particle 1 exerts on particle 2, no, sorry, the other way around, particle 2 exerts on particle 1 is, well, G divided by R squared. The passive gravitational mass of particle 1 times the active gravitational mass of particle 2. But we know, of course, so the same way we can write, right, the force that particle 1 exerts on particle 2, which has the passive gravitational mass of particle 2 and the active gravitational mass of particle 1. But of course, we know from Newton that those two forces must have the same magnitude. So. And from this, we can conclude that the ratio of passive to active mass for both particles will be the same. So GP2 divided by mg, act2. Okay. So we know that they only differ by some constant. In general, so we derived it here from Newton's third law, but in general, this also follows from momentum conservation, right, which is basically nothing else than Newton's law. So if you have a field theory, for example, you can still derive that from momentum conservation. Then we come to the equivalence principle, right, which basically states that all masses must fall the same. It's usually there is this nice story that people tell, right, about Galilei performing this experiment, like with dropping rocks or whatever from the leaning tower in Pisa. Galilei actually never performed this experiment. He didn't really need to perform this experiment. What he did was perform a thought experiment that you, if you have two masses, so assume you have two equal masses. That you drop, then they will obviously fall with the same speed because there is nothing different about them. And now you just bring them closer and closer together, then ultimately you will end up with something that is just basically one block that has twice the mass. But since there is nothing different between this situation and this situation, except that you brought the masses closer together, this must, of course, also fall with the same acceleration. And so, in this way, by this simple thought experiment, Galilei concluded that all masses must actually fall the same. So, if we know this, then then we have the gravitational force, the gravitational acceleration is, well, gravitational force divided by the inertial mass in general, but this is just g divided by r squared. Then we have some large mass that acts as the source. And we have our small mass with its passive gravitational force divided by the inertial mass of this particle. And since this acceleration is supposed to be the same for all masses, for all particles, we see that the ratio of passive gravitational mass and inertial mass must actually also be a constant. So at the end, we have inertial mass that we just call m. We have an active gravitational mass that is some constant time m, and we have a passive gravitational mass that is some other constant times m. So we can just redefine our gravitational constant, right, to be G, C1, C2. And this with this redefined gravitational constant, then all those masses will actually be equal to each other, like the inertial mass. So yes, so basically this equivalence means that Newton's law of gravity can be expressed solely in terms of the inertial mass without any need to giving like specific gravitational masses to different particles. Okay, so yes. As the last section today, before we come to the tutorial that we're supposed to do, first I need a bigger chalk. I want to discuss Einstein's equivalence principle now. And so Einstein's equivalence principle is the foundation of general relativity in some sense. So while that's not a strictly mathematically proven theorem, right? It's usually so in some sense the components of the Einstein equivalence principle are kind of what leads to gravity being best described by a metric theory like general relativity, and the components of the Einstein equivalence principle are the universality of free fall, this is sometimes also called the weak equivalence principle. And that's basically what in Newtonian physics is the equivalent of inertial and gravitational mass. So the universality of free fall states that all test particles starting with the same position and starting in the same direction fall the same way in the gravitational field. So the free fall of all test particles is the same. So of course, in order to test this, you need to know what a test particle is, and there is actually not one defining property of a test particle, but a test particle is kind of a context dependent concept. So you need to require that you don't have any like higher multiple moments, right? That contribute. Usually, you don't want any internal properties like spin or charge, and you want your particle to have a negligible gravitational back reaction. But so what that actually means depends on the situation you want to test. So for example, if you take the Earth-Sun system, then Earth would be, to good approximation, a test particle, while if you take Earth and Moon, that's not true, really. So, okay, so that's the universality of free fall. Then the second component is local Lorentz invariance. Which states that local non-gravitational experiments do not have any preferred time-like or space-like direction. So basically, you can describe local non-gravitational experiments in the framework of special relativity. And the last one is local position invariance. Which usually is translated. So basically, local position invariance tells you that it doesn't matter where in space and where in time you perform an experiment, the outcome will always be the same. And for practical purposes, it's usually translated in two components. The one is the universality of clock rates. So different clocks that move along the same world line. Universality of clock rates. So different clocks moving along the same world line are showing the same time, right? Which is also a bit a statement where you need to be precise. Okay, what qualifies as a clock? So if you have a clock that follows an accelerated world line, for example, then you couldn't use a pendulum clock to show your time properly, right? Because an accelerated pendulum is not a good clock anymore. So you need to think about that a bit and choose a proper clock. And the second component is the universality of gravitational redshift, which basically tells you that all clocks show the same redshift, the redshift that is predicted by general relativity when they are taken along different world lines. So a clock taken along one world line compared to taken along another world line, and then you compare those two clocks by exchanging electromagnetic signals, then the redshift that you see between those two will be that described by general relativity, independent of what clock you use for that. Okay. So I will stop here with the lecture for today, and so we wanted to do a tutorial. So I prepared actually two small exercises. To repeat a bit mainly what we did this morning and maybe build a bit on that. I will just write them down, and then we will see if you have questions, or maybe I give you a little bit of time to think about that, and maybe then we can also still discuss a bit about the lectures. So not all that I have. So the first exercise would be based on the derivation in section 1.2 this morning. So we found from the Klein-Gordon equation, we got the Schrödinger equation, right? So and now the task would be to calculate the corrections of the next order, so of order 1 over c squared corrections to the Schrödinger equation with what we did there in this derivation. And the second task is to study, like this morning we ended a bit abruptly with this Schrödinger-Newton equation. So I wanted to discuss a bit more. You can actually show that it has all the nice properties that the standard Schrödinger equation also has. So, for example, it has a conservation of the norm. So you can actually use psi squared to calculate probabilities. And in particularly, it's also Galilean variant. And we want to show this. So for this, I just write down. So in general, Schrödinger equation with potential B can be shown to follow from a Lagrangian that has the following form: I h bar half psi complex conjugate times psi dot minus psi dot complex conjugate minus h bar squared divided by 2m gradient psi squared minus 1/2 times the potential times modulus psi squared. So you can derive the Schrödinger equation by variation of this by psi star, or yeah, basically giving the Euler-Lagrange equations. So that's the first task, and then I go over there to write the rest. So in general, Galilei transformations can be described by an R4 isomorphism, which is Tx goes to T of Tx, which is, so we get a time shift B. We have, in general, we have a rotation matrix acting on the position plus a boost with some velocity V plus some shift A in position. So this is the general form of Galilei transformations, and it can actually, or you can assume that it acts on a wave function in the following way. So the transformed wave function with this map G will have a phase factor with some time and position dependent phase. And yes. So the circle just means connection of maps, right? And this is the inverse of this diffeomorphism, where so basically your task is to neglect the rotations. So we assume that the rotations are 1, and now task number 1 should be, I call the other one 1, 2. So A is show the covariance Schrödinger-Newton potential. Which is minus gm squared integral d3r prime, sorry, d3y, doesn't really matter, psi of ty modulus squared divided by x minus y. So covariance with respect to this this Galilei transformation G, and B, then I give you the transformations of the time derivative of the wave function, which acts as follows. It gives also the phase factor e to the if. Then we have psi dot after g to the minus 1. This is the velocity vector times gradient psi. And then we have plus I f dot after g to the minus 1. So this you can show, and it can also be shown that the spatial derivative transforms as follows, has the same phase, and then we get the gradient of psi plus I times the gradient of f. And so with this, what is the transformation of the Lagrangian? Okay, just to, sorry, I was wrong before. I don't want you to show that the Schrödinger equation follows from that. That just you can do that for fun if you want to, but the actual tasks are those. So questions, or is it yes? Yes. Yeah. Sorry, what? Yes. On. Yes. Yeah. Yeah. Okay. Yeah. Good point. In principle, you have to include also the gravitational field, right? If you want to, so that would give you, if you do the derivation of the Schrödinger equation or Schrödinger-Newton equation, then you would get higher order corrections from the gravity itself. So if you only look at the non-relativistic order, then it doesn't matter, right? Then it doesn't contribute. But if you want to consider basically relativistic corrections to that, then you need to also include, in principle, you need to include also the gravitational field. But are you asking about the question here? I was, because so this just refers to the free Sangoni. Yes. Sorry. I'm not not sure if I understand the question. So the, yeah, the, yes, yeah, that's my point, content-wise. What it, like what it means, or what it. Um, like you mean if, like when you have the equivalence principle, what do you learn from that? Or the, well, the, yeah, no, I mean basically what you learn. So all those components together, right? You can basically tell. You can kind of. So as I said before, it's not a mathematical theorem in that sense, but you can kind of conclude from that your theory of gravity must be written as a metric theory, right? Like general relativity is written as a theory where like all matter sees the same space-time, right? There is one space-time that with a geometrical structure. So this geometrical property of gravity that you have one metric field that applies to all matter. That's basically a consequence of the equivalence principle. Does that answer your question? If you, sorry. You have to. You mean if you have to make corrections to Euclidean geometry, or like. Well, I mean, Einstein's equivalence principle, of course, leads to GR like we know it, right? So you have a dynamical space-time. But we have seen that like Newtonian gravity with yeah, Minkowski space-time follows as a limit of that, right? And in the same way, the non-relativistic, so the yeah, Galilean variant, Euclidean space-time of classical mechanics follows as a limit from that. So to the amount that those limits are appropriate and are applicable, to that amount, you have, yeah, you also have the okay. Where? In here? Ah, Schrödinger-Newton. Sorry. Yes. Sorry. I'm so familiar to this abbreviation that I don't even notice it anymore. Yes. No. That's yeah. But you don't really. It's this potential. But it's the potential that you have in this Schrödinger-Newton equation that I showed you at the end of the lecture in the morning. So. Yes. Yeah. Yeah, they are actually slow. I don't really know. I think none of the experimentalists is here anymore. So I don't know what the speed is, but the speed is slow enough that you can treat them non-relativistically. I could look it up. Any further questions, remarks? Yes. No, if you have a matter field coupled to the. Yes. Yeah. Just Einstein's equations. Like well, if you have a, like in the way I. Oh, you're talking about the quantized case where you. Well, yeah. Okay. Yeah. Yes. Yeah. Mm-hmm. As long as you couple it in the usual way you couple fields in GR, that does not make sense. I don't. I'm not really sure what you're referring to there, but maybe if you have a quantized field, that can happen. But as long as you have classical fields and you couple them in the usual way, you should not get any violations of the equivalence principle, because I mean that's basically the structure of Einstein's theory, right? You have this geometrical space-time. I mean it's just in Einstein's equations or in Einstein's theory, the equivalence principle is just encoded in this geometrical structure that you. Okay. Okay, I don't know. We can talk about it when you like maybe have a reference or something. Wait. So how do you couple a field? Oh, this is. Yeah. Okay, so you're talking about these. But yeah, but these are modified theories, right? That's somehow modified gravity theory. Yeah. Okay, that may be. Yeah. I don't know much about that. Yes, but it's not general relativity anymore, then, right? It's a modification. Yeah. Okay. Anybody wants to discuss these, or I'm completely open. Actually, we can say we stop for today, and you do that at home. We can also say I do the calculation at the board, or one of you does it. Whatever you prefer. No one looks very excited. Anyone wants to see the calculations of the task? Okay, then I would say we just stop for today, and then yes, see you tomorrow.